Welcome back, everyone, and today we're going to continue on with building King Kai's planet. For a lot of people that don't know, that's a Dragon Ball Z type of reference, and this is really what I want to build. And a lesson or two ago, we used lathe, or we created our lathe to build a sphere, and that's going to be our planet. In today's lesson, we're going to build this road that goes around the planet. And lathe is going to be a pretty useful tool because it's going to be able to build that HUD as well. And we probably be able to build this garage as well on a planet. So our lathe function is going to build a lot of our planet for us. Also probably, trying to think, the bench can probably be extruded, and this... I can't remember what this is, but I think the lathe function will be able to do it too. So the only thing that's going to be problematic is dynamically building these trees, but that's going to be a fun experiment in the future. So that's where we were building, and like I said, today we're building the road. So we got to do some code changes. So the first thing we're going to do is go to fungi extent. And I think when we were doing spheres, when the last lesson we were doing wireframes, we created this new function called triangulate tri strips. That existed in the test page. By this lesson, basically, I just copied it over into extent.mesh because we can always use this again in the future to purposely triangulate something or for doing wireframing again. Another function we're going to add is called vertex offset to the mesh. And all it is you pass in an array, basically two arrays, our vertice array and our array offset. And to make the code very simple, if let's say the array or my vertex array is like 3 components, I pass in an offset array of 3 components. So the idea of offset is to change all the vertices equally by the same amount of distance. If sometimes we have vertice count that goes up to 4 because we use W. So in this instance, when you know you're dealing with 4 vertices, you have to bring in an array of 4. And just make sure that the 4th component is 0, so it doesn't add or subtract anything to that component, unless you really want to. It's, like I said, offset can work any way you need it to. The reason why I did it that way, so I can make this function as simple as possible. So this way I can do I modular length of the offset. So this way I can just keep looping through and just change it. So that's why I built it that way, because it makes the function just a lot more simpler in the long run. I don't have to keep track of certain values or whatever. The last big change for the mesh is triangle strip, because today when we were dealing with our lathe function was always a path. It had a start vertice and an end vertice. Today we're going to create a shape, and the shape will need to be closed. So, we're building like just say we're building a square. So you have your 4 points, right? But the 4th point and the first point need to connect. And so while we're doing triangle strips, that's what I created a new attribute called doClose. So if we're dealing with let's see, if we're dealing with like closed paths, like because we're actually building a shape and not using just a regular line path that's going to be looped around, that comes in handy because we want to connect the last vertice with the first vertice. So we have the doClose, and then we check to see if it is, and then that's all we have to do is just connect pose A and pose B. This part of the if statement as well, in case it's the end or greater than the end, and you do have close, we need to close it. And during any time we're at the end of a row, we need to check to see if we're closing it. So very small changes to just close a path. And those are all the changes to the mesh. Now, I decided to finally do something to dynamic mesh because something was driving me nuts about it. Let me show you. If you remember, this is what the update function used to look like. And we used to deal a lot with managing the vertices, how big the buffer is on the GPU, how much has been pushed to the buffer, and if we're pushing in data that's greater than the size of the buffer we currently have, we kind of resize the buffer on the GPU. You know, we clear out the data and we buffer. So a lot of all of this code just handles one buffer, and then we basically duplicate it again to handle another buffer. And I put a to-do that we should probably make a function or an object that handles the buffer. So this way we're not duplicating this, because down in the future we might need extra buffers dynamically. You know, we're going to need normals, UVs. You know, to have all this duplicated over and over again for every single buffer is going to be insane. So created that object, create a new object, which I'm doing in a different form. Instead of creating a class, I'm building an object dynamically, simply because I'm kind of tired of writing this dot for every little variable. I'm just, you know, every once in a while I'll change styles. For code-wise, it's not smart to change styles a lot of times because you'll confuse other developers that you're working with. But I guess for videos, it's kind of good to switch up styles, so you guys get to learn different ways to write JavaScript. And you guys can pick whatever style suits better for you. So the way this thing is that it's kind of like how the fungi core is put together, where it's like one giant private scope, and that's what I'm kind of doing here. I'm kind of building like a tiny little scoping area. So instead of, you know, doing a constructor and then saying this dot, you know, GL array, this dot buffer reference, and building it out this way, I'm just building them as just regular variables that it lives in the global scope of this function. And then this function returns an object that has a couple of methods in it. And then I have some static functions. So let's go through this really quick. So GL array is going to be a reference to our JavaScript array object. So like here I have commented like a uint1630 uint16 array. That's the array object we need for our index buffer. You could the other thing we'll pass in is probably definitely is the float32 array. So this holds the reference to whatever array we're currently using for this buffer. There's more than just int16 and float32. So this way, we pass in the reference to that class. Buffer reference is really just the ID we get when we create the buffer. So we're going to pass in as the VAO buff attribute. You'll see that in an example later. Just the size of the buffer, and the size of the buffer needs to be calculated. You know, we like I said, this is a reference to that or float32, so we can just say GL array dot bytes per element times component length. Let's sometimes our component length is going to be 3, and sometimes we want 4 for our vertices. Could we use the W component? And then if we're dealing with inst, our component length is going to be 1. So that's going to, it's going to vary a lot. And then you have start size. You're going to be able to start a size, by default. Like maybe you want your buffer to start at 100 vertices, and it'll just calculate it for you. Buffer size used is how much of the buffer is currently being used on the GPU. So let's say if we have a buffer of like 100 vertices, but we only pushed in 98 vertices, that's what the value will be here. So it's 98. So this we can always compare what's being used and what's not being used. buffer type. By default, it's a array buffer, and most often it's always going to be array buffer unless we're dealing with indexed. Then it'll be element array buffer. That, like I said, this is the component length. How big is our component? You know, how many elements in the array does it take to create a single I guess object of information? Like I say, like a vertex. A vertex usually takes three components. It takes 3 floats to build that one kind of object in the array. An M array is actually where we're going to store all our array information. It's basically you know, this dot verts will now be M array in that buffer object. You know, vert size is that is the buffer size, and then vert on GPU is buffer size used. So it's just, like I said, it's just kind of rewriting everything. The names, I think, make more sense now, especially in this context of GL buffer. So let's quickly go through, now that you understand what all the variables are, because I didn't comment what they are all about. The way this is going to be, all this is private, so we can't not access this information outside the object. That's kind of another reason why I did it this way, because if we do objects the other way, like using the class, everything is public, and I kind of want to make these all private. So this way, you can't access this outside the object. These are all private. You can't change it. It can't be modified. It's not accessible at all. So I make M array accessible, but I call it data. So this way, when we're dealing with buffer, data is the array that handles all our vertice information. Buffer size is pretty much the explanation, self-explained. You know, it just returns the buffer size, basically the actual byte size of the data. Get component count is just gets how many components are there. So let's see if we're dealing with an array full of information and the component length is 3. If we divide by 3, we'll basically get the vertice count of that array, because the length of that array is vertice count times 3 if the component length is 3. So sometimes I need to know how many vertices are in there, not how many floats are in there. Set reference is just a way to quickly set the reference. Is a quick setup. You know, we just pass in the variables that we need. And then we have our update function, which is the same as this big mess over here. It's pretty much the same thing. The only difference is using a lot of our reference values. You know, our push, then rename a couple of things like push size, like how much information are we pushing to the GPU? You know, the length times whatever. You know, we set our buffer, we have our buffer reference, we compare the size. If it's less than the actual buffer size, we just push it to the GPU. Else, we save the new size to that. And if there's array data already on the GPU, so like if there's data already being used on the GPU, we're going to wipe it out. And then we're going to push the new data, which then kind of resizes the buffer. We unbind it, and then we just save how much, how many floats did we save into the buffer. And then we have GF buffer float and element, which is just a quick shortcut to setting things up. Because this way we only have to pass in is the buffer reference, the component length, and the start size. And with element, we only need the buffer reference and start size, because element, the component length is 1. So these are kind of just like shortcuts. That's all they are. So this way it kind of fills in array buffer for us, and it fills in float 32. An element fills in element array and the unit and the 1. So this way we don't have to fill this in every single time, because that stuff is pretty standard. So like I said, I made these as two like shortcut starter functions to build up our function, our dynamic GL buffer. So now that I explained how our new GL buffer works. So we kind of don't need all this information anymore that we were storing per buffer. So right now, all I say, okay, well, verts is now a float buffer. I pass in null for reference because I don't know what the reference is yet. I know it's 3 components, and it's a tvert. How big I want the buffer to be, and then yeah, by the end, it's like once we create the VAO, we set the reference, and we do the same thing if we have an index. We create an the element index, set up the shader, and we set the reference. So I think draw has stayed the same. Nothing has changed for that. Clear, I commented this out. I might have to create something else. But for now, I'm just leaving it because I'm not using clear. If I ever use clear, I'll fix this function. And this is what our new update looks like compared to this big, huge mess that I don't like. It's a lot more simplified. We just check to see if there's data. If there's no data, we're just going to set it to invisible false. Else, we're going to set invisible to true every time we do an update. Since the data is in the buffer object itself, we just tell it to update and it'll handle it ourselves or handle it itself. If index is not defined and there is data in there, we tell it to update. We get how many components are in there and we save it to our VAO account. Else, if index does not exist, we want to use verts. So we use verts get component count. Like I said, that sometimes we need to check how many vertices are in there, not how many floats are in there. And that's it. And that is our new dynamic mesh that's much lighter. So this way we can just keep adding more buffers to it without having all this complexity being duplicated over and over again. So that probably took a long time to explain. Now we're going to the fun stuff. Now that we have everything out of the way, adding errors into the code, so we're going to start building our road. We got commented out wireframe because we don't need it. Commented out the sphere. I'm going to add the sphere back in a little later. And I think there's really not much else. So here's an example of what we're doing. We're building this shape. And to do our lathe function, our vertices need to build in clockwise fashion. So we're going to start at this vertex, and we're going to end at that vertex. So we have a function called road, and we're going to pass in an out array that's going to save all our vertices out to it that we're creating. And right now it's all hard coded, but in the future, ideally these 4 values would be passed in, so this way you can dynamically set up the size of your road. So you have your outer width, which is basically the distance between these 2 points, or like between these 2 walls. Outer height, which is the distance between these 2 points. Inner width is the distance between these 2 points, and inner height is the distance between this point and this point, but starting at this position and ending at this position. I'm saying that because every other distance is centered from the origin. So if I have the width, I'm going to divide it by half and then take that half and subtract from 0, which makes it a negative, and it gives me this starting point. And then on the positive end, it'll be on this point. So that's the reason why I'm mentioning that's slightly different. So this way, if I say, this is, a unit of 1 down, it's going to take this point and go down 1 unit. So this way, if we make the height, let's say, 1 unit, but we want the inside to be very deep, we say that's 0.8, and it'll go straight down and be very close to the end. Hopefully I explained it right, and hopefully this is a good enough visual. So right now, in our road function, after we know what our overall dimensions are going to be, we then start calculating our sizes. So it's like I have the out width height, out height half, out width half. That's why I put an H in there. I know all these little numbers, this is not, that's why it's very important to comment. And normally I put a lot of commenting in here, but I'm just prototyping, and this is going to be kind of a throwaway function when I'm done dealing with King's Kai. So I'm not doing as good a documentation as I normally do. So just bear with me. So yeah, object or out with half, because I'm dividing by zero. I'm dividing by half. And again, why am I multiplying by 0.5? CPU wise, it's quicker to do multiplication by 0.5 than is doing a division by 2. So again, it's just tiny little optimization tricks, which it's no big deal for this function because I'm doing so little. But why not just get in that habit sometimes? If you can, do it. Like I said, it's just slightly better to do it in that way to help the CPU out a bit. So now that we know our halves, we just start defining our points. Our left out lower, that's this point. Then we do left out upper, left in upper, and then left in lower. And we just build this part. And that's all I'm going to build for now. Let me save just in case. Now if I go in here, you'll see we defined the points. Those are the points we want. Now what I can do is just, which probably is the better way to do it, is duplicate these in reverse order and then change all the negatives to positives, and that would then create the other half. Or for fun, and in case I ever want to build like a very complicated like if you're going to build like something like this and you can do like 1/2 and then you want to basically mirror it, you can do like this. To do a quick mirror dynamically, you just like you do a loop, but you do it backwards. So if the array is, this is 0, 1, 2, 3, then I take that information and loop it backwards. So I go 3, 2, 1, 0. And so, like I said, I'm starting at the length of -3, because you got to remember, I'm going by vertices, and each vertex is 3 components. I'm going to loop by -3 till I become 0. So as I'm looping through the array I just created backwards, I'm switching the negative state on the x-axis. So the y-axis, the z-axis stays the same, but I'm flipping the x. So this way, this becomes this becomes that becomes that, and that becomes that. Nice quick way. So if we have like if for some reason we dynamically create like maybe like 50 points because we're creating some very complicated mesh, and we do it on the left side, then this single line of code can be used to mirror it on the left side. So this way you don't have to add an extra 50 pushes. And like I said, you need to build this in order for us to triangulate. So that's why it's being done this way. So I build half of it, then I use that loop to mirror it. So now that it's mirrored, refresh. Now it exists on the other side. Beautiful. So that's our road function. That's all we needed for the road function. Now that we got our paths put together, I'm surprised it doesn't give me an error. Now we're going to do the offset, because we're going to want to rotate this on the x-axis. But for us to rotate it properly, because if we rotate it the way it is, it's going to rotate on the origin, and that's not going to make the mesh that we need. It's going to make a big mess. So what we need to do is to move our path as much as we want. So I'm going to move it 2 units up. See, now it's in the air. So this way, when I start looping it, it loops this way from around the origin. All right, so what else? So can I just comment this part out? So to make that possible, I need to see. I was pushing everything into our new GL buffer, dynamic buffer. So now to make this really work with the lathe, I need to push everything into the path array. I need to offset our path, and our path would be pushed into lathe, and the data will be saved into our vertex buffer instead. Now we refresh. Now it's probably hard for you to see, but now you can see that it's been repeated in a circular fashion around the origin. So this way, if you want, you can then change the offset. Just say it's 1 unit. Refresh. Now it's tightly packed together. And just so you can see what it looks like if I don't add any offset at all, let me just comment that out. Ends up being this big mess together. Boom. Yeah. So once we start triangulating, and if it's like this, it's garbage, you know. So that's why I created this vertex offset. So this way, if you're building, let's say if you're building, like the road function is just the part where we build the path, the starting path that we're going to extrude. So that's basically, that's what we're doing. We're using the lathe function to extrude it, to make copies of it in a certain path or certain pattern. So let me give it offset too. So by changing the offset, we're moving it so if we're going to have a function that's building a road, after you have these parameters, you can then say, well, how, because we're building a circular road, mind you. This normal road wouldn't be circular. You might end up using a Bezier curve to build the road. But since I'm building a circular road, I can use the lathe function. So this way, like if I was going to build like a function called round planet road, I would then pass in what is my radius, like how do I want it to spin around in a circle. All right, so the next thing is we just triangulate everything. And the only thing we need to do is, since now we're triangulating all the data, we need to change our draw mode to triangle strips. Granted, we're not triangulating. I'm sorry. We're taking our lathe data and creating our triangle strip index from it. So we pass in, the index, which is how many vertices I think it is, or include like how many times you want to loop around the circle. So it's 3 times, and then how big is the path, and then here's our index data. True. Don't remember what those are, but yeah, we wrote these functions, so we should know what they are. So now that we set it up as a triangle strip, and we set the mode, and we have that. Now it should be able to render our shape beautifully. Now let's use a better material. Let's use our low poly material. Refresh. There we go. And there's our path. We can see it very better now that we have lighting and whatnot. Now, some of you might be like, well, that doesn't look like a circle. It doesn't look like a round planet. But that's okay. Let's see. So let's change that to 5. If I remember correctly, is that how you do it? Boom. There you go. Now we're, like I said, we're rotating on the x-axis, so we can repeat it as many times as we want, and we have our triangulate function. This is a very low poly circle road. You know what? If I wanted this to be really good, you know what? Let's do 40, because I think that's all we need. Refresh, and there you go. Looks like a ring. But there you go. Like how quickly we were able to quickly change the shape. You know, we went from like this kind of triangle shape. Now it's a nice circular shape because we're just extruding it with a larger increment, or maybe a smaller increment technically. You know, more copies tightly packed together. And for fun and giggles, I'm going to uncomment our sphere. Oops. I don't need that. Save, refresh. And there you go. We have our sphere. Now you might say, well, that doesn't look right. It doesn't look anything like that. Of course it doesn't, because I'm just prototyping at the moment. So this is where I'm going to end it for now. But as you can see, we've got a road. And don't forget, this road is dynamic. I can change the width, the height, dimensions as any way I want to. So ideally, in probably future lessons, I'll probably just show you once I'm done, like putting it together. Like I'll take the sphere, I'll define how detailed I want it, and then you know, like how big do I want it and things like that. Because it's this size right now, it's like only 2 units big, but I might end up. Let me see, how do I do this? I might eventually make it huge. That will take up much more of the grid space. So this way I can put trees and a house and things like that. So yeah, so first of all, I need to make the sphere bigger, define how detailed I want it to look like, because I want to play with shaders. And then once I have that size, then I take what I have now and then slowly change the settings, the widths, the heights, and the dimensions of that path, so it fits perfectly on the planet to kind of create this look. And the only thing, so that's it. That's the plan. So we got the planet, we got the road. The house is going to be easy. It's really mostly just half a circle. So that's easy to kind of just create a path and then lerp it. This one will be kind of easy to do too. It's kind of half circle with a line, with some lines. It kind of just goes down, and then we just have to extrude it once and then triangulate. Unless I want to try to do something funny. Like I said, everything I'm going to do for this planet is not going to be modeled with a 3D tool. Everything's going to be procedurally generated. So that's really the goal of this milestone, is to build up the engine and get enough experience doing procedurally generated content. It's not going to be No Man's Sky, but it's going to be a nice beginning of No Man's Sky. Our first planet is going to be King Kai's planet, because it's a nice, small, simple planet to generate dynamically. I'm not going to create dynamic textures, in case you're wondering. Maybe I will. Who knows? I've started prototyping that, by the way. Yes, I have. So that's it for today's lesson. The next thing I'm going to do is, now that we have two objects, I need to really start working on transformation hierarchy. A long time ago, we put in parent-child placeholders for our transform object. Now it's time to really flesh out the idea. So this way, I can make the road a child of the planet, and if I move the planet or rotate the planet, the road will then move and rotate based on the position of the planet. So this way, instead of, like right now, I need to move both objects separately. If I had them built in a hierarchy, like I said, I only need to move the planet and everything that's attached to the planet as a child, automatically gets moved and rotated along with it. So that's going to be probably our next lesson, and that's going to be a little bit complicated. So the next lesson might take a little while before it comes out, because I need to. I researched it, but I need to prototype it because there's so many different ways to go about it. There's different names for it. There's triangulate hierarchy. Another popular name for it is called a scene graph. And there's a lot of issues. Like my original idea, then I start reading more about it. It's like, oh wait, that complicates things. No point wasting this video about some of that, because I'll talk about it when I actually do it. But so that's really what the next lesson is about, is start doing parent-child relationships and having all the matrices compound and add up together. So that's going to be fun. So that allows us to do more fun things, especially since, like I said, we're building King's Kai's planet. We need the house, we need the trees, we need all these little objects on the planet. And when we rotate the planet, maybe have a little script that just does like a slow rotation. We want everything to rotate with it in one go. So this way we don't have to sit there and loop through all the objects to do that. So yeah, there we go. There's our road, and you can do, like I said, any path will do. You can do any circular path you want. Like I said, if you do like a circle path, then you make a donut. You can always use that road function with the previous lesson with the Bezier curves. So you can actually take the road path, apply it to our Bezier curve functionality that we built a couple of lessons ago, and you can actually design your own roads, like actual roads for video games. So now you finally have all the pieces to actually build that if you want dynamically. The only thing that's really missing is UVs, which is kind of complicated to apply a UV to a road. There's some videos about that you can look up that kind of talk about different ways to apply UVs, but they use Unity. So Unity kind of gets away with a lot of stuff. So yeah, I know I've said this several times. That's it for the video. So this is officially, that's it for the video. I'm worse than Steve Jobs. One more thing, or one last thing. So again, like, subscribe. See you guys at the next lesson.